So I think linear probing was bad when we really were tight on space, but when you can afford a factor of 2, linear probing is great. That's the bottom line. Now, this is totally random, not so useful. What about all these other hash functions, like universal? Turns out, with the universal hash function, linear probing is really, really bad, and that's why it gets a bad rap. But some good news. Okay, first result was log n-wise independence. This is extremely strong, but it also implies constant expected per operation. Not very exciting. The big breakthrough was in 2007 that 5-wise independence is enough. And this is why this paper, Thorpe, was focusing in particular on the case of k equals 5. Actually, they were doing k equals 4, but they solved 5 at the same time. And so you can get, this was a highly optimized, practical, all that good stuff. Get 5-wise independence, admittedly with some space, but it's pretty cool. And so this is enough to get constant expected. I shouldn't write order 1 because I'm not writing the dependence on epsilon here. I don't know exactly what it is, but it's some constant depending on epsilon. And then this turns out to be tight. There are 4-wise independent hash functions, including the ones, I think the polynomial ones that we did, these guys, that are really bad. You can get, really bad. They're as bad as binary search trees. You can get constant expected. So you really need 5-wise independence. It's kind of weird, but it's true. And the other fun fact is that simple tabulation hashing also achieves constant, and here it's known that it's also 1 over epsilon squared. So it's just as good as totally random simple tabulation hashing, which is nice because again, this is simple, takes a bit of space, but both of these have that property, and so these are good ways to use linear probing in particular. So you really need a good hash function for linear probing to work out. If you use a universal hash function like a times x mod p mod m, it will fail. But if you use a good hash function, which we're now getting to the point, this is super simple to implement, should work fine. I think it'd be a neat project to take Python or something that has hash tables deep inside it, replace, I think they use quadratic probing and universal hash functions. If you instead use linear probing and simple tabulation hashing, might do the same, might do better, I don't know. It's interesting. It would be a project to try out. Cool. Well, I just quoted results. What I'd like to do is prove something like this to you. Totally random hash functions imply some constant expected. I won't try to work out the dependence on epsilon, because it's actually a pretty clean proof. Looks nice. Very data structures-y. I'm not going to cover Knuth's proof. I'm essentially covering this proof. The 5-wise, in this paper, 5-wise independence implies constant expected. They reprove the totally random case and strengthen it, analyze the independence they need. But let's just do totally random implies constant expected for linear probing. Okay, we obviously know how to do constant expected already with other fancy techniques, but linear probing seems really bad, yet I claim not so much. And we're going to assume m is at least 3 times n. That will just make the analysis cleaner, but it does hold for 1 plus epsilon. Okay, so here's the idea. We're going to take our array, our hash table, it's an array, and build a binary tree on it, because that's what we like to do. We do this in every lecture, pretty much. So this is kind of like ordered file maintenance, I guess. This is just a conceptual tree. We're not even defining an algorithm based on this, because the algorithm is linear probing. You go into somewhere, you hop, 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 hop until you find a blank space, you put your item there. Okay, but each of these nodes defines an interval in the array, as we know. So I'm going to call a node dangerous if essentially if its density is at least 2/3. Now the expect, but not in the literal sense, because there's a little bit of a subtlety here. There's the location where a key wants to live, which is h of that key, and there's the location that it ended up living. I care more about the first one, because that's what I understand. The h of x, that's going to be nice. It's totally random. So h of x is random, independent of everything else. Great. Where x ends up being, that depends on other keys, and it depends on this linear thing, which I'm trying to understand. So I just want to talk about the number of keys that hash via h to the interval, if that is at least 2/3 times the length of the interval. This is the number of slots that are actually there. Okay, we expect the number of keys that hash via h to the interval to be 1/3. So the expectation would be 1/3 the length of the interval. If it happens to be 2/3, it could happen because of high probability, whatever. That's a dangerous node. That's the definition. Those ones we worry will be very expensive. And we worry that we're going to get super clustering and then get these giant runs and so on. So, okay, one thing I wanted to compute was what's the probability of this happening. Probability of a node being dangerous. Well, we can again use turn-off bounds here because we're in the totally random situation. So this is the probability that the number of things that went there was bigger than twice the expectation. The expectation is 1/3, 2/3 is twice of 1/3. So this is the probability that you're at least twice the mean, which by turn-off is small. It comes out to e to the mu over 2 to the 2 mu. Great. So this is e over 4 to the mu. You can check e. It's 2.71828. So this is less than 1. Kind of roughly a half-ish. So this is good. This is something like 1 over 2 to the mu. What's mu? Should know that. Mu is 1/3, 2 to the h for a height h node. Okay, it depends how high you are. If you're at a leaf, h is 0. So you expect 1/3 of an element there. As you go up, you expect more elements to hash there, of course. Okay, so this gives us some measure in terms of this h of what's going on. But it's actually doubly exponential in h. So this is a very small probability. You go up a few levels. Like after log n levels, it's a polynomially small probability of happening. Because then 2 to the log n is log n, and then e over 4 to the log n is about n. Okay. But at small levels, this may happen near the leaves. All right, so now I want to look at a run in the table. These are the things I have trouble thinking about because runs tend to get bigger and we worry about them. This is now, as items are actually stored at the table, when do I have a bunch of consecutive items in there that happen to end up in consecutive slots? So I'm worried about how long that run is. So let's look at its logarithm. Okay, and round to nearest power of 2. So let's say it has length about 2 to the L. Sorry, plus 1. between 2 to the L and 2 to the L plus 1. Okay, so look at that. And it's spanned by some number of nodes of height h equals L minus 3. Okay, so there's some interval that happens to be a run, meaning all of these slots are occupied. And that's 2 to the 2, I guess. And so I'd go to level -1. A little hard to do in a small picture. But we're worried about when this is really big, more than some constant. Okay, so let's suppose I was looking at this level. Then this interval is spanned in particular by these 2 nodes. Now it's a little sloppy because this node contains some non-interval, non-run stuff, and so does this one. At the next level down, it would be this one, and this one, which is a little more precise, but it's never going to be quite perfect. But just take all the nodes you need to completely cover the run. Then this will be at least 8 nodes, because, I mean, the length is 2 to the L. We went 3 levels down. 2 to the 3 is 8. So if it's perfectly aligned, it will be exactly 8 nodes. In the worst case, it could be as much as 17, because potentially we're 2 to the L plus 1, which means we have 16 nodes if we're perfectly aligned, but then if you shift it over, it might be 1 more because of the slop. Okay, but some constant number of nodes. It's important that it's at least 8. That's what we need. Actually, we just need that it's at least 5, but 8 is the nearest power of 2, rounding up. Cool. So there they are. Now, I want to look at the first 4 nodes of these 8 to 12 nodes. So first meaning leftmost, earliest in the run. So if you think about them, so there's some 4 nodes. Each of them spans some, I should draw these properly. What we know is that these guys are entirely filled with items. The run occupies here. It's got to be at least 1 item into here, but the rest of this could be empty. The interval keeps going to the right, so we know that all of these are completely filled with items somehow. So let's start with how many there are, I guess. They span more than 3 times 2 to the h slots of the run. So somehow, 3 times 2 to the h, 3, because there's 3 of them that are completely filled, otherwise it would be 4. Somehow 3 times 2 to the h items ended up here. Now, how did they end up here? Notice there's a blank space right here. This was by definition, this is the beginning of a run, meaning the previous slot is empty, which means all of the keys that wanted to live from here to the left got to. So if we're just thinking about the keys that ended up in this interval, they had to initially hash to somewhere in here. H put them somewhere in this interval, and then they may have moved to the right, but they'd never moved to the left by linear hashing if you're not completely full. So because there was a blank spot here, none of these keys could have fallen over to here. We have no deletions. Okay? So you're doing insertions. If they may have spread it out, and they may have gone farther to the right, or they may have filled in gaps, whatever. But H put them in this interval. Okay. Now, I claim that in fact, at least one of these nodes must be dangerous. Now, dangerous is tricky because dangerous is talking about where H puts nodes. But we just said we've got to be at least 3 times 2 to the H keys where H put them within these 4 nodes. Otherwise, they wouldn't have filled in here. Now, if none of those nodes were dangerous, then we'll get a contradiction. Because none of them were dangerous, this means at most 4 times 2/3 times 2 to the h keys hash via h to them. Why? Because there's 4 of the nodes. Each of them, if it's not dangerous, it has at most 2/3 of its size. Keys hashing there. 4 times 2/3 is 8/3, which is less than 9/3, which is 3. Okay, so this would be a contradiction because we just argued that at least 3 times 2 to the h nodes have to hash via h to somewhere in these nodes. They might have hashed, well, they might hash here and then fallen over to here. So there is this kind of, things can move to the right, we've got to worry about it. But just look 3 levels up and it's okay. So one of these nodes, not necessarily all of them, are dangerous. And we can use that to finish our analysis. This is good news because it says that if we have a run, which is something that's hard to think about because nodes are moving around to form a run, so keys are moving around to form a run, we can charge it to a dangerous node, which is easy to think about because that's just talking about where keys hash via h, and h is totally random. There's a loss of a factor of 17 potentially, but it's a constant factor, no big deal. If we look at the probability that the length of a run, say containing some key x, has length between 2 to the L and 2 to the L plus 1, this is going to be at most 17 times the probability of a node at height L minus 3 is dangerous. Because we know one of them is, and so just to be sloppy, it's at most the sum of the probabilities that any of them is, then potentially there's a run of that length, and so union bound, it's at most 17 times probability of this happening. Now, all the nodes look the same because we have a totally random hash function. So we just say any node at height L minus 3. And we already computed that probability. That was this. Probability of being dangerous was e over 4 to the 1/3 2 to the h. So this is going to be 17, or at most 17 times e over 4 to the 2 to the L minus 3 power. Okay, again, doubly exponential in L. So if we want to compute the expected run length, we can just expand out the definition. Well, let's round it to powers of 2. It could be the run length is about 2 to the L within a constant factor of 2 to the L. And so it's going to be that times the probability, well, this probability. But this thing is basically 1 over 2 to the 2 to the L. And so the whole thing is constant. This is L, I mean, L could go to infinity. I don't really care. Because this is, I mean, this gets dwarfed by the double exponential. So this is super geometric. So very low probability of getting long runs. As we said, after log n size, or after, yeah, it's very unlikely to get a run longer than log m. We proved that in particular. But in particular, you compute the expected run length. It's constant. Okay, now this, of course, assumed totally random. It's harder to prove. Where were we? Somewhere, linear probing. It's harder to prove 5-wise independence is enough, but it's true. And it's much harder to prove simple tabulation hashing works, but it's true. And so we can use them. So this gives you some intuition for why it's really not that bad. And similar proof techniques are used for the 5-wise independence. Other fun facts, you can do a similar caching trick that we did before. Again, the worst run is going to be, I don't know, log or log over log log. I don't have it written here. But if you cache the last, it's not quite enough to do the last log n, but if you cache the last log to the 1 plus epsilon n queries, so a little bit more, then you can generalize this argument. And so at least for totally random hash functions, you get constant amortized with high probability. This weird thing that I've never seen before. But it's comforting because expected bounds are not so great, but you get it with high probability bound as long as you're willing to average over log to the 1 plus epsilon different queries, as long as you can remember them. And the proof is basically the same, except now instead of looking at the length of a run containing x, you're looking at the length of the run containing one of these log to the 1 plus epsilon n nodes. That's your batch. And you do the same thing, but now do it with high probability analysis. But again, because the expectation is now bigger than log, you expect there to be a lot of fairly long runs here, but that's okay because on average it's good. You expect to pay log to the 1 plus epsilon for log to the 1 plus epsilon queries. And so then you divide and amortize and you're done. So a little bit more details in the notes about that if you want to read. I want to do one more topic, unless there are questions about linear probing. So, yeah.
So could you motivate why the pick value of mu is the mean for whatever quantity?
So mu is defined to be the mean of whatever quantity we're analyzing. And the Chernoff bound says probability that you're at least something times the mean is the formula we wrote last time. Now here, we're measuring, I didn't write what the left-hand side was, but here we're measuring what's the probability that the number of keys that hash via h to the interval is at least 2/3 the length of the interval. Now, if m is at least, or let's say m equals 3n, then the expected number of keys that hash via h to the interval is 1/3 times the length of the interval. Because we have a totally random thing, and we have a density of 1/3 overall. So you expect there to be 1/3, and so dangerous is when you're more than twice that. And so it's twice mu. Mu is, in this case, 1/3 the length of the interval, and that's why I wrote that.
Okay, so this comes from the m is greater than or equal to 3n.
Yeah, it comes from m equals 3n and totally random.
So some of these equalities should be like...
Yeah, okay, let's make this equal. Make this more formal. It's an assumption anyway, so to simplify the proof. Good. Change that in the notes too. Cool. So then the expectation is exactly 1/3 instead of at most 1/3, so it's all a little cleaner. Of course, this all works when m is at least 1 plus epsilon times n, but then you get a dependence on epsilon. Other questions? So bottom line is linear probing is actually good. Quadratic probing, double hashing, all those fancy things are also good, but they're really tuned for the case when your table's almost full. They get a better dependence on epsilon, which is how close to the bound you are. And so if you're constant factor away from space-bound, linear probing is just fine, as long as you have enough independence, admittedly. Double hashing, I believe, gets around that. It does not need so much independence. Okay, but instead of going to double hashing, I'm going to go to something kind of related to double hashing, which is cuckoo hashing. Cuckoo hashing is a weird idea. It's kind of a more extreme form of perfect hashing. It says, look, I want to... perfect hashing did 2 hash queries. So I did 1 hash evaluation, another hash evaluation. Follow it, which is OK. But again, I want my queries to only do 2 things, 2 probes. So it's going to take that concept of just 2. And actually use two hash tables. So we've got B over here. And we've got A over here. And we're going to have, if you have a key X, you hash it to a particular spot in A via G, and you hash it to a particular spot in B via H. So I have 2 hash tables, 2 hash functions. To do a query, you look at A of G of X, and you look at B of H of X. Oh, sorry, I forgot to mention, the other great thing about linear probing is that its cache performance is so great. This is why it runs so fast in practice, why it's only 10% slower than a memory access. Because once you access a single slot, you get B slots in a cache with block size B. So most of the time, because your runs are very short, you will find your answer immediately. So that's why we kind of prefer linear probing in practice over all the other schemes I'm going to talk about. Well, cuckoo hashing is all right, because it's only going to look at 2 places, and that's it. It doesn't go anywhere else. So kind of like, I guess with perfect hashing, the thing is, you have more than 2 hash functions. You have the first hash function, which sends you to the first table. Then you look up a second hash function. Using that hash function, you rehash your value x. Downside of that is you can't compute those 2 hash functions in parallel. So if you're like 2 cores, you could compute these 2 in parallel, look them both up simultaneously. So in that sense, you save a factor of 2 with some parallelism. Now, the weird thing is the way we do an insertion. You try to put it in the A slot, I guess, or the B slot. If either of them is empty, you're golden. If neither of them are empty, you've got to kick out whoever's there. So let's say if you kicked out Y from its A slot, so we ended up putting X in this one, and so we end up kicking Y from wherever it belonged, then you move it to B of H of Y. There's only one other place that that item can go, so you put it there instead. Okay. In general, think about a key. It has 2 places it can go. There's some slot in A, some slot in B. You can think of this as an edge in a bipartite graph. So you make vertices for the A slots, vertices for the B slots. Each edge is an item, a key. Key can only live in 1 spot in A, 1 spot in B for this query to work. So what's happening is if both of these are full, you take whoever is currently here and put them over in their corresponding slot over in B. Now that one might be full, which means you've got to kick that guy to wherever he belongs in A, and so on. If eventually you find an empty slot, great, you're done. This chain reaction of cuckoo steps, I guess, where the bird's going from in and out, or from A to B, vice versa. If it terminates, you're happy. If it doesn't terminate, you're in trouble because you might get a cycle or a few kind of failure situations. In that case, you're screwed. There is no cuckoo hash table that works for your set of keys. In that case, you pick another hash function, rebuild from scratch. So it's kind of a weird hashing scheme because it can fail catastrophically Fortunately, it doesn't happen too often. So it still rubs me a funny way. I don't know what to say about it, but okay. So you lose a factor of 2 in space. It's 2 deterministic probes for a query. That's good news. It's all right. Now we get to what about updates? So if it's fully random or log n y is independent, then you get constant expected update, which is what we want, even with the rebuilding cost. So you'll have to rebuild about every n squared insertions you do. The way they say this is there's a 1 over n build failure probability. There's a 1 over n chance that your key set will be completely unsustainable. If you want to put all n keys into this table, there's a 1 over n chance that it will be impossible, and then you have to start over. So amortized per insertion, that's about 1 over n squared. Insertions you can do before the whole thing falls apart, and you have to rebuild. So it's definitely going to be amortized. This should be amortized expected, I guess. However you want to think about it. But it's another way to do constant amortized expected. Cool. The other thing that's known is that 6y's independence is not enough. This was actually a project in this class, I believe the first time it was offered in 2003. 6y's independence is not sufficient to get constant expected bound. You can have it will actually fail with high probability if you only have 6y's independence. What's not known is, do you need constant independence or log n independence? With log n, very low failure probability. With 6y's, high probability you fail. Like you fail with probability 1 minus 1 over n. Not so good. That's good. Some good news is simple tabulation hashing. Means you will fail to build with probability not 1 over n, but 1 over n to the 1/3 power. So this is a little, and this is theta, this is tight. It's almost as good as this. We really only need constant here. This is to build the entire table. So in this case, you can insert like n to the 4/3 items before your table self-destructs. So simple tabulation hashing is, again, pretty good. That's I think the hardest result in this paper from last year. Yeah. So I do have a proof of this one. Something like that, or part of a proof. Let me give you a rough idea how this works. So if you have a fully random hash function, the main concern is that what if this path is really long? I claim that if an insert follows a path of length k, or the probability of this happening is actually at most 1 over 2 to the k. It's very small, exponentially small in k. And to give you, I just want to sketch how this works because it's a cool argument that's actually in this simple tabulation paper. So the idea is the following. You have some really long path. What I'm going to give you is a way to encode the hash values or the hash functions. Okay, how many? There's hash functions g and h. Each of them has n values. Each of those values is log m bits. right? So if I just wrote them down the obvious way, it's 2 n log m bits to write down those hash functions. Now, we're assuming these are totally random hash functions, which means you need this many bits. But I claim that if you follow a path of length k, I can find a new encoding scheme, a way to write down g and h that is basically minus k. This many bits minus k. I get to save k bits. Now, it turns out that can happen, but it happens only with probability 1 over 2 to the k. This is an information theoretic argument. You might get lucky, and the 8 g's and h's you're trying to encode can be done with a few fewer bits, k fewer bits, but that will only happen with probability 1 over 2 to the k if g and h are totally random. So how do you do it, basically? I want to encode the things on the path slightly cheaper. I'm going to save 1 bit per node on the path. So what do I need to do? Well, the idea is, okay, I will start by writing down this hash value. Okay, this takes log m bits to write down that hash value. Then I'll write down this hash value. That takes log m bits, log m bits. Generally, is going to be roughly k log n to write down all of the node hash values. Then I need to say that it's actually x, this particular key that corresponds to this edge. So I've got to write that down. That's going to take log n bits to say that x is the guy for the first edge, then y is the key that corresponds to the second edge of the path, then z, then w. But nicely, things are ordered here. So it only takes me log n, k log n, to write down all these guys. So I get k times log m plus log n. Now, if m is 2 times n, this is k times 2, times 2 log m minus 1. So I get 1 bit of savings per k, per thing in the path, essentially because it's easier for me to write down these labels to say, oh, it's the key x that's going here. Instead of having to write down slot names all the time, which cost log m bits, writing down key names only takes log n bits, which is a savings of 1 bit per thing on the path. And so, well, that's a quick sketch of how this proof goes. But it's kind of neat. It's an information theoretic argument why the paths can't get long. You don't have to worry about cycles and things that look like this. It's kind of messy, but same kind of argument generalizes. So that was your quick overview of lots of hashing stuff.